Hello and welcome back to Yeyu Lab. The latest version of Google's Gemini 2.5 Pro just dropped. It's impressive, especially in the multi-step reasoning, coding, and long context, and its performance on the benchmark is so impressive than the other mainstream models. The key is it still cannot handle audio output, with only supported data type for output is text. So if you're building anything that needs real-time audio, even with images, you are stuck using the older Gemini 2.0 Flash EXP model for now. Just like what we have done before, when we use the Live API, the only model that we can use is Gemini 2.0 Flash EXP, which is an experimental model, free for use but with limitations. I've been sharing tutorials on building different things with Gemini Multimodal Live API, from the camera app to screen sharing applications, but there's still an annoying problem with the Flash experimental model is that it still has some pretty strict limits. If we move down on its documentation, you will see you only have 2 minutes for audio and video applications and 15 minutes for audio only applications. There's no way around it, even if you are willing to pay for more sessions or more tokens for a certain API key. Once time's up, the connection drops and the model forgets anything. Always Flash start every time. You may remember that I have made a video about using RAG system to build a document searching chatbot using the Gemini's Multimodal Live API plus the Llama index system for RAG functionality. Here I want to explain why regular RAG isn't good enough for our voice assistant. First, basic RAG is pretty bad at finding right information from personal conversations. It messes all the subtle things, the way people phrase things differently, the context that build up over time. Second, saving entire conversations gets messy fast. The storage adds up very quickly. You can imagine when the whole conversation will be saved. Third, basic RAG doesn't get how things connect. It treats everything like separate pieces of information instead of seeing how concepts building on each other. For a tutor or teacher that in our demo today, that really helps you to learn, we need something better. We need something that understands what you're talking about, tracks how you are learning, and changes its approach based on what works for you. That's where Mem0 framework comes in. So what is this framework and what makes it so different? The Mem0 is a smart memory system, especially for AI applications. It's not just storing information, it's understanding it by using LLM as well. Here's what it does. It gets meaning, not just words. Mem0 uses embeddings and graphs to understand what conversation is actually about. It sees connections. It keeps tracking of how different ideas and memories link together so it can follow how you understand growth. And recently they add the support for the graph database. For graph memory, that's managing the relationship tracking between different concepts and memories, which really showing how your knowledge grows over time. And also its usage of its open source version is very simple. Just a few steps, including installation and initial memory, add memory, then retrieve your memory for a simplest application. If you want to expand, you can also choose different vector store series or LLM configuration, embedded configuration, and graphic store configuration. So let's see the demo. Let me simulate a learning assistant based on the similar front end that we have used before to share the screen and talk to the model. Let me first share a screen of a sign function. Okay, I have difficulty to understand the sign function in the trigonometry questions. Can you help me to understand shortly?
Okay, I see you're having some trouble with the sine function in trigonometry. Let's break it down. The sine function, often written as sin theta, is a fundamental concept in trigonometry that relates an angle of a right triangle to the ratio of the length of the side opposite to the angle to the length of the hypotenuse. Do you have any specific questions you have about the sine function? Or would you like me to explain further some parts of this definition, like the relationship between the angle, the opposite side, and the hypotenuse?
Okay, I finished the conversation and stopped the server, which simulates a session timeout that's generated by Google Gemini due to its rate limit. Normally, the model will forget all our historical conversations. So let's see how the memory helps in this situation. You can see before we end the server, there has been a new memory added in the system. That indicates I have difficulty understanding the sine function in trigonometry questions. So let's restart the server and refresh the web page. Share the screen again. Hey, can we continue our last discussion about my difficulty in understanding some math problems?
Okay, I recall from our previous discussion that you were having some difficulty understanding the sine function, specifically in the context of trigonometry. Is that still where you're feeling stuck?
Yeah, can you give me some examples and then continue with the cosine function?
Sure, we can definitely look at some examples of the sine function and then move on to the cosine function. Before we dive into examples, would you like a quick review of the sine function's definition, just to make sure we're on the same page?
Hey, I have difficulties to understand the difference between the sine and cosine function.
Okay, I understand. You're having some trouble understanding the difference between the sine and cosine functions. Let's start with the basics. Both sine and cosine are trigonometric functions that describe the relationship between the angles and sides of a right triangle. However, they relate to different sides. In a right triangle, if you consider one of the acute angles, let's call it x. The sine of x, written as sin x, is the ratio of the length of the side opposite to the angle x divided by the length of the hypotenuse. The cosine of x, written as cos x, is the ratio of the length of the side adjacent to the angle x divided by the length of the hypotenuse. Does that make sense so far?
Okay, let me stop the service and restart it again to simulate again the Gemini's session limit. And refresh the page to see whether the model still remember what we have talked about before. Hey, do you still remember our recent discussion about some topics in trigonometry questions?
Yes, I remember that we recently discussed the difference between the sine and cosine functions. Do you have any follow-up questions about that, or would you like to discuss a new trigonometry topic?
Now let's check out the system diagram to understand how the system works. It's divided into two main sections, the client part and the server part. The client is very normal, just like what we have done before for almost all the Gemini applications, that there's a microphone and the screen sharing widget to capture the audio and images from the user side. and the data is sent to the WebSocket in the browser. The WebSocket also received the synthesized audio from the server, which is then played through the speaker and show the text output on the web page also. The key parts is the Python server. The Gemini session handler is the center component on the server. It manages the connections to the Gemini API and orchestrates the entire process. The Gemini Multimodal Live API section represents the interaction with the Google Gemini endpoints. It receives the audio and image data from the client. When the Gemini model needs information from the user past interactions, it makes a tool call we called query memory to the Mem0 components. The Mem0 components received the relevant. The Mem0 components retrieves relevant memories and send them back to the Gemini API. The Gemini API then generates a text and audio response, which is sent back to the Gemini session handler. There is also another path that shows the audio transcription process, which also including the memory storage process. First, the user audio data that's received from the client will be directly sent to a convert PCM to wave component, and that component converts the raw audio into a wave format that is acceptable by the Gemini 1.5 Flash model to do the simple transcription task. And the transcribed text will be sent to the add to Mem0 function blocks, which we use the Mem0 to store the historical conversations into the vector stores managed by Mem0 framework. In another path, when the Gemini's audio response generated, it will be also sent to the convert PCM to wave component and use the same functionality to transcribe the audio data and send that transcribed text to match that user message with the assistant message in a pairs to store in the Mem0 vector store management. And meanwhile, the assistant audio will send back to the client together with the text response that's generated also by the transcription module to make it visualized from the user's browser. So the key enabling of this personalized and context-aware tutoring is the Mem0 components, which store the conversation history and let the system to retrieve the memories by demands. Okay, now let's move to the code walkthrough. In this section, I will provide a detailed walkthrough of the server-side Python code, explain how the Gemini Multimodal Live API and Mem0 and audio transcription are integrated into a personalized tutoring assistant. Again, the front-end part has no difference from I showed in the previous demos, so you can download directly from my GitHub repository that's listed in the description below. So here I will focus on the functionality description for the server-side implementation. So first, you should provide the Google API key as usual to enable all the Gemini model usage. And here, this model is for the Multimodal Live API that enabled the voice and image chat in this project. So here I will put aside of this Mem0 configurations in the later Mem0 description. First, I will still introduce again about the Gemini Multimodal Live API connection. In the Gemini session handler, this function established a connection to the Gemini Multimodal Live API and all the bridging functions that implements the real-time multimodal interaction. Here we define a client. That's the instance of the GenAI client class initiated by your API key, and the client AIO Live Connect is the method that creates a live bidirectional connection to the Gemini API. Like I said before, the model here is the Gemini 2.0 Flash EXP model, which is the only model, even it's in the experimental stage, that is the only model that supports the multimodal live interaction so far. And we should also provide the config, which basically including the system instruction that I ask the model to behave like a math tutor that answering questions, but should check out the memory by using of the tool to see whether we have discussed the similar topics and concepts before with this student. If they found, they will use that as a background and reference to support the continuous tutoring. If there's no relevant past discussion I found, it will start from the fundamental explanation. And the tools should be one of the most important parts in the config that pass to the model, whose schema has been defined here with the only parameters that's called query with a string format to let the model to input the query string to search the memory. And the implementation of the function is here to use the Mem0 functionality to search in the memory that we will introduce later. So push that tools into the model, and then the model will understand what function need to be called before they give a response. When the WebSocket connection has been established, let's see the send to Gemini function, which handles the sending data to Gemini API. It received images from the WebSocket connection and forwards them to Gemini endpoints using the session send to bridge the data from the client to the Google Gemini. And here we provide two different type of the mem type. One is the audio PCM, the other is the image MPEG or other types that's supported by Gemini. If it's a text input, which we have not enabled in this project, it also will bridge that text data into the Gemini endpoint. Now let's see the receive from Gemini function, which handles the receiving data from Gemini API. It uses a synchronous loop to iterate over the responses received from the session receive method. If there's some server content contains in the model's response other than the normal text and audio, it will check if it's the tool core information contains about any tool calls made by the model decision. In the normal case, the model will call the query memory that we defined in the configuration, and with a generated query string to ask you to make a real query memory. And if it's normal 10 messages and including the supported type of data, especially that is the audio data, it will forward the data to the client via the WebSocket connections with the client by using the WebSocket send. The WebSocket is something that we initializes here to establish the connection between the backend to the front end. Don't mess up with the WebSocket connections between the backend to the Gemini Multimodal endpoints. It's the connection between the backend to the front end that we exposed to the public IP and the custom port 9084 for client to connect. So let's look back to the tool call process. Here we know when the Gemini wants to use a tool, it sends a tool call object in the response, and the code extracts the function name and arguments from the tool call object, use that to execute the actual function to query the memory. Send back the memories in list back to Gemini by using this format that's defined by Gemini's function call responses, with the name of the function, response, and the result object, and ID with the function call ID to match the function request. Here I also restructured the memories list from the Mem0 because it's too much complicated with unnecessary data like the time and other IDs. Just leave the pure string with the top 10 scored search results to the Gemini. And this function response data will be sent back to the Gemini by using the session send again to let the Gemini to generate the real audio responses. Now let's see the transcription process continued by the receiving of Gemini's audio responses here. So whatever there is a valid user audio or assistant audio, we will all push that audio data into the convert PCM to wave function to take the raw PCM audio data received from the client or the Gemini and converts it to a base 64 encoded wave file here. And we should be a little bit careful about the difference between the input sample rate and output sample rate, because the input from our user's front end is 16K Hertz, but the response from the Gemini Multimodal Live API is 24K Hertz. Just make sure you follow this code to use the right sample rate. And that output wave data will be fed into the transcribe audio function, which takes these base 64 encoded wave audio data and transcribes it into text using Gemini 1.5 Flash or Gemini 2.0 Flash Lite. Such kind of lightweight model is enough for the transcription, and their fast speed is our most preference for the transcription task. So here I just give a very simple prompt, generate a transcription of the speed, and do not include any other text in the response. And if you cannot hear the speech, please only say not recognizable. So it's quite stable for this simple task. Now let's see the Mem0 part of how we implement the memory storage, management, retrieval, and other things. At the top of the code, there is a configuration object that specified the embedding model, the LLM retrieval model, and the vector store to enable the basic process of the memory management. Here I use the embedder provided by Gemini and its new embedding model EXP March the 7th to do the backend embedding process. I'm using also the Gemini model 2.0 Flash to do the memory summarization and query, and the vector store I use the default quadrant server that's deployed locally with a port 6333. If you don't know how to set up a quadrant server, you can check out the Mem0 documentation to find its quick start with the Docker to install and run locally with the Qdron storage. Then we set up the memory by using the Mem0's memory function from config to read the config into object memory, and defined a fixed user that's needed by the memory management. In the add to memory function, we add the conversation that represented as a list of messages to Mem0. It takes the messages and a user ID and optional metadata tutoring session that's used to support the categorization of the memory. And the query memory function that searches the Mem0 by using the memory search function for relevant memories based on the query and a user ID. It returns a list of the memories that match the query with some scores and other parameters. So that's all for the code. If you can build a front-end service that connect via the WebSocket to a server deployed on the port 9084 or any other port that you custom in the code. And if you don't know the send and receive format, you can refer here that you can see the format is very simple, including the send and receive between the front end and back end for the audio and text data. Okay, so when your system starts, you can check in your log to find out the memory process controlled by the Mem0. For example, here, when there is a conversation, we will adding to the memory with the message pair using the raw user and content that transcribed from our audio input, and also the assistant output that transcribed to the model's output audio. So I have said, hey, I have difficulties to understand the difference between the sine and cosine function, and here is the model's output to explain the sine and cosine. And when these message lists feeds to the Mem0, it will add to the memory by using the LLM to summarize, hey, you have a memory that's having trouble understanding the difference between the sine and cosine function, and add that memory into the memory system. So when the next time you restart the session, you will see the total receive triggered at beginning by query the trigonometry question that triggered by the user's audio input, and the memory retrieved from the system will include that memory piece to say, I have trouble understanding the difference between the sine and cosine function with a metadata tutorial session category, and the score is relatively high. And we will send this function response to the Gemini by restrict the output into a pure string with a memory summary. If we have a lot of memory summary extracted, we will list it in the sequence based on the score data. Okay, that's the basic usage of the long-term memory especially for the conversation data. So when combining the power of Gemini's multimodal API with these kind of intelligent memory capabilities, we can create truly personalized multimodal experiences that adapt to the individual needs of each user. So anyway, this is just a beginning, and I'm excited to see what you can build with the components. That's all for today. Leave your comments, and I will see you in the next video.